Hey everyone, good morning, good afternoon, and good evening to you wherever you are. It is my pleasure to virtually meet you all once again in this year's Open Source Firmware Conference. Now it's too bad that we are still unable to meet and connect with each other physically, but as usual, we do not worry about things that we cannot control. Hopefully, we'll meet again next year. My name is Yah Wen, and together with my colleague Sai Kiran, we are from the Intel Internet of Things group. Both of us will be sharing with you how Slim Bootloader turned fantastic in this pandemic. In today's sharing, we are going to cover several topics. For those who are new to Slim Bootloader, I will be doing a quick recap of our previous OSFC presentations and brief introduction of what is Slim Bootloader. After that, my colleague Sai will be sharing with you the exciting new features that we have added since our last OSFC sharing. Finally, we'll end the presentation telling you about the future plans for Slim Bootloader before concluding the sharing with a call to action. Let's begin with a quick recap. Slim Bootloader has a special relationship with OSFC because it was about 3 years ago in Germany. That's the time and place we officially announced and launched Slim Bootloader to the community. A year later, in OSFC 2019 San Francisco, we shared about the additional Slim Bootloader's capabilities, as well as a tutorial session on how to easily port Slim Bootloader to your own Intel-based custom hardware. If you missed both events, worry not. You still can access the material and replay the recordings of the 2019 event in OSFC's YouTube channel. Now, if you are new to Slim Bootloader, please allow me to give you a brief introduction of what it is. Slim Bootloader is a boot firmware that is originally designed for IoT use cases that provides ease of implementation, fast boot capabilities, and it comes default with security features built in, like verified and measured boot out of the box. It is also extensible, scalable, and open source with permissible licensing. Slim Bootloader also leverages Intel firmware support package and is now expandable to other modern applications such as smart edge computing, industrial use cases, retail, and many more. Now, if you look at Slim Bootloader in a nutshell, this is what it is. If you do a git pull from our open source repo, you get all of these except for the alternative payloads, which is colored in yellow. So Slim Bootloader supports multiple OS that Intel has validated, for example, Windows, Yocto, Linux, Ubuntu, Android, and even hypervisors like Acorn. Now, by default, Slim Bootloader comes with the OS Loader payload, which launches the Linux OS kernel directly, and it also has a firmware update capability as a form of a payload. With some speed optimizations, you are allowed to change and tweak Slim Bootloader to suit your fast boot requirements. And for the firmware update, it comes with fail-safe firmware update mechanism so that it won't break your system when you are doing a firmware update process. And as I mentioned earlier, it comes integrated with security features and supports Intel BootGuard, verified boot, secure boot from reset vector all the way to the handoff to the OS. And to configure Slim Bootloader, as well as the FSP parameters, it comes with a configuration editor tool that you can easily select what are the options and what are the settings that you need to tweak and change. And all of these are supported in the Intel architecture platforms all the way from Atom to Xeon. So how do we make it fantastic in this pandemic? First and foremost, the silicon and platform supported has been added ever since we last presented in OSFC 2019. Right now, the silicon and the platforms that is highlighted in this red box, we have now supported the Whiskey Lake Silicon for both Intel CRB and also the Aeon Up Extreme Developer Board. We have supported two variants of Comet Lake Silicon with the Intel RVP, Tiger Lake, both U and H in both the RVP as well as the Up Extreme i11. And recently we launched the Elkhart Lake, the 6000 series atom-based silicon. And for this silicon, we supported both the Intel CRB and just recently, in fact, just few days ago, Aeon Up Squared 6000 was just launched, and we are ready to upstream our patches to support this developer board as soon as it's available. Other than that, for the virtual platform, we have added support for the CMix QSP. Now, all of these support is the URL is provided in this table. So once you get this slide, you can click on the link to know where are the information available for this. Right now, I would like to pass the time over to my colleague Sai to tell you what are the new features that we have added so far. Over to you, my friend Sai.
Thanks, Yah Wen. Are you able to hear me?
Yes.
Yes, sure. Thanks, Yah Wen, for the introduction there. So I'll just go through a list of some nice features that were added into the Slim Bootloader in the past 1.5 years. So the first one is firmware update. Today's boot firmware images come with several subregions included in them, like LAN region, ME or a CSME region, the BIOS region itself, and so on and so forth. So Slim Bootloader allows for updating these components individually via Slim Bootloader, concept called Slim Bootloader containers. Now, we do not need to update an entire boot firmware image if only a section of it needs an update. And this is exactly the motivation behind the individual components update. And as a part of this, the ME or the CSME firmware is also updatable when it is passed as a component in the capsule. The Slim Bootloader's firmware update payload can identify it and call the respective CSME or the ME update driver to do the job for it. And we'll see in detail about what a container is and how we can pass the capsule, the container inside a capsule in a later slide in detail. And one other feature for firmware update is about how it is triggered from the Linux. For this, the Linux kernel, a new Linux kernel driver was added into the kernel, which exposes a device attribute to the user in the user space so that he can set it to trigger the firmware update. And once the reboot is done, Slim Bootloader can identify this trigger and launch the firmware update payload. And a link has been given for this newly added Linux kernel driver here. Moving on, additional payload support. Slim Bootloader, when it launched initially, as Yah Wen mentioned already, came with an inbuilt OS loader payload, which could boot your Linux kernel like vmlinux, busy image, or other ELF images and multi-boot images. And also there was support for internal UEFI-based EDK2 payload, now which could launch your traditional UEFI Windows and other UEFI-based OSs. Now, in addition to those payloads, we have added support for 3 new payloads. One is iPXE for network boot. So traditional UEFI-based EDK2 payload could also do the job for us in this case, but it required other network stack drivers and an UNDI driver to be added to support that. But iPXE project, which is open source right now, provides a ready-made solution for us in this regard. And Slim Bootloader has support for loading and launching this iPXE payload, which could boot most of the popular live Linux ISO images that are available today. And there's a specification called Universal UEFI Payload Spec, which provides a universal API so that any bootloader can boot any payload that supports this API. For example, Core Boot can boot Linux payload with following this API, and Slim Bootloader can boot other UEFI payload or Linux boot or U-boot, etc. Slim Bootloader has also support for this universal UEFI payload-based API. And third one, MicroPython. MicroPython is a lean and efficient implementation of the Python programming language, and it contains a subset of the Python standard library. And this can be built as an individual component and loaded as a payload from Slim Bootloader so that you could boot to the MicroPython shell and run your Python scripts from there. Next. Functional safety. So there is something called a pre-OS checker, which actually launches before booting to your traditional OS and checks for the system state and whether Slim Bootloader or any bootloader for that matter has performed some initialization tasks correctly. Now, the pre-OS checker binary itself, this comes in the form of binary, and the binary itself is not a part of the Slim Bootloader, but Slim Bootloader has support to load and launch this kind of pre-OS checkers, and then upon its success, automatically fall back to booting your traditional OS. Now, this pre-OS checker can be FUSA certifiable, and it is currently available in El Catholic platform. I guess Yah Wen can give you more details about this if you have questions about that. Now, moving on to the next one, 64-bit support. Slim Bootloader has updated its build infrastructure to build 64-bit images. So right after the temp RAM initialization by the FSP, we set up the page tables, the level 4 page tables, specifically speaking, to support the 64-bit boot. And we can jump right into the 64-bit mode from stage 1A, which is the first execution of C code in the Slim Bootloader. Now, one important point to observe here is the FSP still does not support 64-bit builds, and it still ships 32-bit binaries. And the Slim Bootloader has to thunk into the 32-bit mode to call FSP API, and then thunk back to 64-bit mode. And this occurs seamlessly today in the Slim Bootloader, and we can run from in 64-bit from stage 1A all the way to the place where we hand off to the OS. And advanced PCI features. So if we think of a scenario like cloud service providers, where they operate huge servers, and generally these servers are multi-socket systems that come with huge amounts of RAM installed and more complex PCI routing on the hardware when compared to their client counterparts. In order to support this, the Slim Bootloader's PCI enumeration library has added to support multiple root bridges, wherein we expose a policy to the user where he can configure what buses the user can scan and what control he can do with the allocation of the memory and the IO resources for those root bridges. For example, he wants to downgrade to 32-bit for one particular bus or a list of buses, and downgrade to 64-bit or something like that. And one important feature for the servers is the IO virtualization. In order to support this, Slim Bootloader's PC enumeration library has support for SR-IOV and the ARI protocols, which are industry standard specifications. If the user can enable these features in the static configuration, the Slim Bootloader's PC enumeration can identify the SR-IOV and the ARI capable devices and enumerate all the virtual functions and assign the memory and the PCI memory and the IO resources for them accordingly. And PCI hot plug support. Today, for the platforms that are available in the open source, PCI hot plug is supported in the form of the ACPI code that is needed. And also when FSP exposes the required UPDs, Slim Bootloader has a way for the user to configure the bifurcation and the hot plug and the power management settings to support this. Next. Next one is enhanced debugging capabilities. So there is something called Intel System Studio, which is publicly available, which is a cross-platform tool suite that contains the Intel Studio debugger, which allows us the capabilities like system debug and system trace. Now, Intel Studio Debugger, which is the system debug part, is an Eclipse integrated editor debug software that can help us with an in-depth Slim Bootloader source code debug and also the SOC peripheral registers. And the system trace can help us with the execution and the capturing, the extracting, and the analysis of the system traces from hardware, firmware, software, and other sources via the Intel Trace Hub. Now, one a salient feature in this is that the Intel Studio Debugger has a support to break at reset for Slim Bootloader, which means that we can debug Slim Bootloader source right from where it starts execution. And also Studio Debugger allows to load the symbols for the Slim Bootloader and also view the source code while debugging, that is the C source code while debugging. And how is the actual setup done for debugging? Requires multiple steps on the side of the target, that is target configuration, enabling some hardware features like DCI and etc. And how the actual the connection between the host and the target for debugging, and also some host side configuration like the system studio debugger configuration. And all these details are given in the Slim Bootloader's GitHub documentation page, and a link has been provided here. Now, a real-time support. Time coordinated computing TCC has been a major feature in the Intel chips recently. Now, what this involves is tuning and customization of some real-time KPI for specific workloads. So how is the tuning, how is the customization done and communicated back to the silicon initialization code so that it could boot in a different way and give us a better KPI, is how the firmware update is done for this TCC related binary blobs. And we shall see in the next slide how we can do this effectively using the Slim Bootloader containers. And configuration. Ease of platform and boot configuration has always been a central part of design goals of SBL. And as a part of this, Slim Bootloader maintains a centralized configuration database where it can be improved, updated, validated, and verified for security, optimized for its performance and its footprint. And as a part of enhancing this configuration database, we have moved all the configuration related files into YAML syntax, and a GUI-based setup has also been added into the Slim Bootloader. So if a user can select the SBL to boot to the GUI-based setup, he can select so in the static configuration, and a nice GUI is launched wherein you can change your configuration settings, and the settings get written to the NVRAM, the SPI flash, and on the reboot, you can see the new changes taking effect. Now, a CLI-based and standardized stitching script for each platform means that each platform today, which is open source, has got a stitching script, which will take the all different parts or regions of the boot firmware image as inputs and stitches a nice boot firmware image that can actually boot on the board. Next. Now, we have spoken a little about how the firmware update process is done using the SPL component container. Basically, a container has been designed keeping in mind as an encapsulation of independently updatable and verifiable components. So if you can see the picture on the right side, there is a container header and offsets to each component, and there is a container header public key and signature. And the components themselves have a header, like a decompression header, and the component image, the payload itself, and the public key and the signature. Now, if we can look at a use case, this makes more sense to us. For example, if we need to verify effectively an OS image can traditionally contain a kernel and an init RD and a command line. So these three can be treated as three different components. They can be signed in a different way. They can have different kinds of decompression, etc. Now, if they all can be multiple components in one single container, it will be easy for us to verify the OS image as a whole, or it will be easy for us to verify each component of the container individually based on their decompression and based on their types of signing, etc. And let's say for firmware update, we have seen what a pre-OS checker is and what TCC config blobs are. So if we have to do the tuning and the customization for TCC, for example, then we can send the TCC config blobs as they are all related into one single container as multiple components. And the Slim Bootloader's firmware update payload can identify this container, parse it, get the individual components and update those components in the firmware flash for us. And extended payload, we can provide user with a choice to boot to what payload dynamically. If we can give them a list of payloads already in the boot flash, they can do this via a GPIO pin to select what kind of payload they want or any other way. But since all the payloads are logically similar, they can be put as multiple components in the container and can be verified before launching each payload. Next one, please. Some other security enhancements to name. Slim Bootloader initially supported 2K key signing, so we have added 3K key signing now. And in addition to the already existing SHA-256 hash algorithm, we have added SHA-384 and SM3. And for SHA-256, we had optimization in the hardware in the form of the SHA-256-NI instructions. And for the newly added payloads, we also have an optimized C source code for better performance for calculating hash. And signing script enhancement. So Slim Bootloader had multiple signing scripts, but we brought all of them together in a single script. For example, container signing and capsule signing, etc., so that the signing process has been simplified for the user. There is one place to go for signing. And also we support multiple hash algorithms, and we also support using a local key or a key from the remote server from signing. And regarding to the firmware support, package support, Slim Bootloader today has support for up till the firmware FSP 2.3 version. Yeah, that there ends my list. Back to Yah Wen. Thanks, Yah Wen.
Thanks, Sai. So as you can see, we have worked out pretty hard in this pandemic to make Slim Bootloader better by adding new features and enhancing it and making it simpler so that customers and also the open source community can try it out and apply it on their own Intel-based custom hardware with Slim Bootloader. So what's next? What's coming up next for Slim Bootloader, right? So as Intel, we will continue to add support for future Intel Silicon as they are released, and also the associated platforms that comes with it, either the CRP or the RVP or even the developer board. If it's available, we'll try our best. Now, there will be continuous enhancement on Slim Bootloader with regards to features, if it's something that makes sense and that helps our customer, makes it easier for Slim Bootloader to be adopted. Of course, we'll try our best to add it, and we'll continue to improve on our online documentation, which as of date is already quite comprehensive, and also thanks to all the feedback from the community. So more feedback is welcome. So last but not least, we will continue to strive for better code quality improvements. And of course, with the evolution of FSP coming up, please do refer to Vincent Zimmer's talk on universal scalable firmware, which is also available in this year's OSFC, to know more about it. And Slim Bootloader is ready to support these new FSP updates when they are available. So call to action. So if you haven't done so, please do try out Slim Bootloader and let us know how we can improve it, make it better, make it simpler, make it more configurable to your business needs or to whatever that you seem is suitable for you, right? And of course, please do participate and contribute back to the open source community of Slim Bootloader. Intel truly appreciates all your valuable feedback and contributions. And for the past a year or more, we have been pretty busy answering questions in our mailing list and looking at all the different PRs in our open source. So we really appreciate all of that. So here are some of the links that you can go to if you're interested. Of course, the main Slim Bootloader webpage is in intel.com/SPL. For the source and the repo, you can go to the GitHub page of SPL. Documentation links are also there. And last but not least, please do participate in the mailing list. If you have questions, if you have suggestions for improvement, please join this groups.io mailing list, and yeah, shoot us a question and we'll try our best to answer them at our best capability. And with that, we would like to end this presentation. And if you have any questions, feel free to ask us and we'll try our best to answer. Thank you so much. And thank you, Sai.